There's one other wild card associated with sea level rise that really falls well outside of any of the projections, and that's because we really don't know how to evaluate the probability of this occurring. This is the large collapse of ice from East and West Antarctica associated with the loss of one of the large ice shelves. This is a picture of the Ross Ice Shelf. It's an enormous piece of floating ice. And remember, it's floating, and that means that 90% of it is actually below sea level. The Ross Ice Shelf is located on the Ross Sea, covering a good part of the Ross Sea. It's essentially land ice that has drifted out over the ocean and is now floating over seawater. But unlike sea ice, which is very thin, maybe just a few meters at most, the Ross Ice Shelf averages about 1,500 meters thick. So this is an enormous piece of ice. Because it's floating in the ocean, breaking off of a large ice shelf isn't actually going to change sea level directly. We've actually seen ice shelves along the Antarctic Peninsula break off. In particular, the Larsen B ice shelf was very dramatic as it happened over just a period of a few days. But when a big ice shelf like that breaks off, it doesn't cause sea level to rise directly because it's already floating on the ocean. It's already displacing seawater. The reason that the breakup of a large ice shelf is important is because it actually allows for the rapid flow of ice from Antarctica into the ocean. The way you can think about it is that these large ice shelves, both the Ross Ice Shelf over the Ross Sea and the Ronne Ice Shelf just across the way next to the Antarctic Peninsula, what they're doing is they're actually acting like the buttresses in a cathedral. They're actually holding back the large ice sheets that are sitting on land. In the case of East and West Antarctica, there are very fast ice streams that are supplying ice into the Ross Ice Shelf. If you were to break off the entire Ross Ice Shelf and have it disintegrate and float out into the ocean, what would happen is, essentially it's like pulling the cork out of the bottle. Suddenly, huge amounts of ice would flow into the Ross Sea and leave as icebergs. And you could imagine a very large amount of ice being discharged over a very short amount of time. Instead of a very slow sea level rise of maybe a few centimeters over a century, you could actually see a meter of ice loss or maybe even more from Antarctica in 100 years. And remember that there's over 50 meters of sea level equivalent stored in Antarctica total. So this is actually just a tiny fragment of what's possible in the centuries to come. One of the points here is that we actually don't really know how to evaluate the possibility of this happening. Scientists tend to be very conservative. So when we talk about something like the collapse of the Ross Ice Shelf, we like to use statistics. We like to try to use data and estimate the probability of something like this happening. But we've never seen anything like this before. And our models aren't nearly good enough to explain exactly how this might occur. Worse than that, we actually don't even have very good observations of the Ross Ice Shelf. Some of our best observations of what's happening underneath the Ross Ice Shelf actually come from thermometers strapped to seals that very clever biologists have used to try to understand the conditions in which these animals live. Now that's a little bit funny, but it's actually a little sad in that our observing systems are so bad that we're really flying blind in this one. If the Ross Ice Shelf were actually breaking up today, it's not clear that we would know about it. In general, we tend to ignore or at least de-emphasize these very uncertain situations, like the breakup of the Ross Ice Shelf. I'm not trying to suggest that the Ross Ice Shelf is certain to break up. It's going to break up at some point as the Earth warms, but I certainly don't expect it to happen in the next 100 years. The point is that I really have no idea, nor does anyone else, when it's going to collapse. We often treat these sorts of possibilities as high consequence, low probability events. In fact, they're really unknown probability events. We just have no idea whether they're going to occur or not. And the difference is actually very important. We tend to assume that they're low probability, and therefore, even though they're very high consequence, we don't have to worry about them very much. But in fact, they might be already fated to happen. In fact, they may be happening right now. We just don't know. This just emphasizes how much we don't understand about the climate system and how it's going to respond as the Earth warms. It's possible that the ice shelf will stay there for many centuries and that Antarctica will still be stable for thousands and thousands of years. But it's also possible that the acceleration of ice loss will be dramatic and that the Ross Ice Shelf might break off starting tomorrow, and we could see a dramatic acceleration of ice discharge. We just don't know. One thing we can say for sure is that the scale of these ice sheets are so massive that it's hard to imagine any way that we could engineer to actually stop the collapse of the West Antarctic ice sheet or the East Antarctic ice sheet if the Ross Ice Shelf did break away. We're tinkering with processes at a scale that's enormous, and it's hard to imagine how we could put all these pieces back together if something did start to go awry.